So this is the we have total 3 examples based on doubly reinforced concrete beams. We like to find the capacity, the bending capacity of these reinforced concrete beams. So this is kind of, you can say, analysis. There are 2 kinds, as Heather mentions. This is analysis. In the analysis, you have given the steel reo or compression reo, beam, the width of the beam, depth of the beam, all the geometric dimensions and those other dimensions are given, and they will ask you to find the capacity of your beam. Another one is the design, where they will give you this design capacity like M star, and then you figure it out, this AST or ASS. So there are 2 kinds. Either they have give you the B and D and you find the reinforcement, they will give you all the details and you find the capacity. Otherwise, they will give you the design moment and then you figure it out, the reinforcement. So this is first, which is analysis, where you need to find this MUU. We have 600 millimeter by 350 millimeter doubly reinforced sections. FC dash equal to 32. There is a stirrups, R10 stirrups, that stirrups here sitting here, that is given 30 millimeter cover. So from this stirrup to here is 30 millimeters, and from here to here this cover is 60 millimeters. Now, by the way, how do we know whether this one is doubly reinforced or not? So I think when you have to have these, when I take you the examples, I think they will give you more details. Let's start giving these solving this example. So of course we need to solve some of these details. Let me tell you something. The main thing that we need to follow is the same strategy that last week. Oh, by the way, there is some details here that you can go through it. I don't want to read it, but they are just whatever. I will go through it one by one. So what is the strategy here? We will have a strain first, either in the concrete and steel. From the strain, you will get the stress. From the stress, you will get the force. You will get means you will calculate the forces and then you will calculate the moment. Right? That is the analysis procedure we follow. How are you going to know the strain? The standard will tell you that the concrete has this strain. How are you going to find the yield strength? 0.025. You said okay to 500 divide by 200 yield strength. So you will get this strain. Once you know the strain from the stress state diagram, you can calculate the stress in the concrete, and then stress in the concrete is 500 megapascal for steel, right? If it is on the yield. So once you know the strain, then you just multiply by area of the concrete, multiply by area of the steel. If it is compression, then you multiply by this, you can get the forces. And once you know the force, you multiply by the respective distance. Let's say DC, D, and so on. So you can calculate the MUO. So that's the overall procedure. Among this one, the main troublemakers is always DN, depth of the neutral axis. We need to somehow find the depth of the neutral axis, either singly reinforced or doubly reinforced. Once you know the DN value, then our life is significantly, or we can solve these examples in a simple manner. There are a couple of checks that we need to make that I will tell you in as we solve. So let's start solving these examples. So what we have given, this is given. Let me draw that one. So we have given these cross sections here. We have given this top reo, and then we have given you this 8 with the spacer bar. Right, and then we have a stirrups as well. We have stirrups. All right, so now based on that one, we need to have a strain value. So now here we're going to add one more, like this. We're going to add one more, meaning that last times we have this. If you remember that, we have this EST. And then we have this 0.003 strain in the concrete. This is a strain in the tension reinforcement. And we have this depth of the neutral axis. That is the unknown value all the time. Now we have one more addition, which is this one. What is that? This is the strain in the compression reinforcement. That is then additional component. Last week we have only two strain, EST, which is the tensile, and another one is 0.03. But today lectures we added one more strain, so that is going to add one more component. And then we have a stress. Yes, the stress is almost the same story that like last times. You have these alpha 2 FC dash, and then you have these let's say blue color one. Let's say this is tension. Let's say this is concrete compression, and there is a one more, by the way, that we're going to do it is this Rio. This is steel Rio. Let's say steel in compression. So you have three now, and then you can calculate the moment MUO with the capacity factors. So let's same procedures, that MUO equal to this force T times by distance, some distance. We will tell you where we're going to take the moment. Then this CC, because one would be minus or plus, we will say which side we are taking. Basically, we're going to have a three force, and we have three distances that we're going to work it out. So that's the overall procedures that I just captured. Now to do this one, we need to crack some of these new things. Okay, now let's do the first one. Area of steel in compressions. Right, let's get this one out first. So let's denote it by area of steel in compression equal to how many bars we got? We got 2N28 bars. Okay, 2N28 bars. You can go in these tables. 2N28 1232 millimeter square, right? So that's good. So we can put this 1232 millimeter square because we have 2N28 bar, and we can get it from Rio data table. So that's first area of the bottom stop Rio is done. Now let's say area of steel in tension. Let's denote it by AST. How many bars we got in the bottom Rio? We have a 8N28 bars. 8N24 bars, not 28. So we can go back here. 8N. So we have 8, 24, and if I just cross it out here, they will meet here. So 3616 millimeter square. So 3616 millimeter square, because we have how many? 8 and by the way is the ductility class. Okay, Rio data table. Alright, so area of the steel done, area of the board steel is done. Now let's work out these small d and capital D. So what happens here? We have this. By the way, let's go back to that figure here, because we already have this. So let's say we give them name this depth of the top Rio as a DSC, and let's give them this. This small d. Right, we done it many times, this one, so that is small d, effective depth. Now let's work out DSC. DSC meaning is depth of the compression Rio. Now the DSC that you can get it from cover. What is the cover here? That cover is top one is 60 millimeters. Let's put it that 60 millimeters. Plus that cover plus this stirrup. How much stirrup we got? R10. So we have 10 millimeter stirrups. Plus we have this Rio red one. What is the Rio? 28 Rio. So halfway through, right? Halfway through of 28. So that would be 28 millimeter divided by 2. So if you use calculator, 60 plus 10, 70, 84 millimeters. If everyone agree with me that the top Rio, that top Rio here, 2 Rio, they are sitting at, from the top one is 84 millimeters, right? That's I hope you don't have any issue to calculate that one. Small d. Now this small d is, we done it many times, but I think there is some trick here that we need to find, that this small d would be from the center of the spacer bar. So how do we find that? We will take the whole capital D first. How much was that? Is 600. So let's say that is whole big capital D is 600. So let's get that 600 millimeters. Take away the cover. Take away cover meaning this distance. How much cover we got? Cover we got bottom 30 millimeters. So 60 millimeter, take away 30 millimeter. Then we will take these stirrups 10 millimeters. I think we done the stirrup 10 millimeters just now. So we put 10 millimeters. Then this Rio, the big Rio that here, the bottom layer of the Rio, that is 24 millimeters. So let's take it 24 millimeters, take away 24 millimeters. And then we need to go through halfway through that spacer bar. So if I go through halfway through the spacer bar, and the spacer bar is 32, so we just need to make it 16 millimeters, or let's say 32 divided by 2. 32 millimeter divided by 2. So if I just simplify that, I would get 520 millimeters. So what we done so far? So far we calculate the area of the steel compression, easy, area of the steel in tensions, and we find the distance from the top of the beam to the compression Rio and small d, which is the tension Rio. And there are two factors that we always needed, if you remember, that are friendly, alpha 2, and if you go back to the standard on section number 8, we are working on section number 8. If you come back to the clause 8.1.3, and on that clause you can see alpha 2 equal to 0.85, 0.015 FC dash, alpha 2 is greater than 0.67. So that's fine. Let me copy that. 0.85 take away 0.0015 FC dash. So 0.85 take away 0.015 times by FC dash. What was the FC dash we got? Let me close this one, 32 megapascals. So that's fine. This is empirical equation, so the unit does not comes into the pictures. So if I use the calculators, it will tell me 0.802, which is greater than 0.67. Therefore alpha 2 is okay. All check is okay. We can take alpha 2 equal to 0.82, and gamma is also given just down here, 0.97 take away 0.025 FC dash, and gamma as well greater than 0.67. So I would have a 0.97 take away 0.025 FC dash. So we just multiply by 32, empirical equations, unit does not count, so you get 0.89 by using the calculators, we get 0.67, therefore gamma check is okay. We can take gamma value equal to 0.88. Now we need to make some assumptions that that look, these steels which is in the red, the top Rio, should be at yield. Okay, it's not at yield, but we need to make an assumptions right now, and we're gonna make it check, because of course it's very close to the DN value. Look at this, DN is very close to this one compared to here, so of course it will not gonna yield, right? If you are closer to, if the steel Rio sitting next close to the DN value, depth of the neutral axis, it will not gonna yield. I'm sure it will not yield. I'm 100% sure that these will not yield. So I would like to make a very bold assumptions. Bold assumption meaning that it will not gonna work. Let's say ASC, which is the stop Rio, is at yield. Okay, let's for mathematical reasons, let's assume that we have that yield and we're going to check later. Let's say we're going to check later, right? We need to make sure that it's not yielded, and if it's not yielded, what would we going to do it? Let's assume that for mathematics, it's at yield. So if at yield, then force, then compression force. Let's assume at yield, compression force in top Rio or compression Rio equal to, the force is equal to stress of the Rio times by the area of the Rio, right? Now stress is a yield stress because we make a assumption, so that is FSY, and if it is at yield and if you use N bars, we have 500 megapascals, which is basically Newton per millimeter square, times by area of the top Rio we calculated 1232 millimeter square. So you have 1232 millimeter square. So if you use the calculators, you will get 616,000 Newton force that are taken by the top Rio, right? But the condition is they should be at yield. Okay. So this is the first one. Let's say how much compression force taken by force in concrete. Let's say how much compression. Look, there are three components here, right? Top Rio, concrete, and tensile Rio. So all three components will contribute into the moment. So we just need to get that value. So basically this is stress and this is your area. Remember last week in the lectures I explained you how you get this area and so on. So alpha 2 was 0.802, 32 megapascals concrete strength. Gamma value we get is 0.89. Dn we need to find. B value we have given 350. Right, so let's plug that value. So we have 350 millimeters. Right, so if you just plug into the calculators, you get 7994.336 dn. Right, so that's the dn that we're going to calculate. Now, tension force in bottom Rio. Right. So basically, I'm just calculating there are top Rio and there are 8 bottom Rio. So this is the force which is which we calculated. Let's say this force is CS. This force is CS. This concrete one, that is CC, and this one here, which is, let me put the value as a tension. So this is tension force. So we just calculating the tension force. Again, of course this bottom wall will be yielded. That is no doubt about it, because the area of the steel in the bottom Rio we have calculated 3616 millimeter square. So 3616 millimeter square times 500 Newton per millimeter square, or we can make it megapascals. So if you just calculate that, you will get 1808000 newtons, right? So now equilibrium. Now this beam is not horizontally equilibrium, right? All these forces, let's say compression forces are going. This is compression force going here, compression force going here, and tension force going on this side. So let's say some of the forces in the x directions. Let's say horizontal equilibrium, horizontal force equilibrium, right? Because this beam should be in equilibrium. All these forces, compression force and tension force, should be in equilibrium, meaning that all summed up they will give you the zero, the value that you get it. So let's say this is tension force positive. So 1808,000 Newton positive going left to right. These are two negatives. Let's say this concrete one, compression force negatives 7994.366 dN, and let's say there is another compression force which is not right, but let's try it, 61600 Newton equal to 0, right? So what happens here? I have three forces. One is this force is going bottom 1808,000 newtons, and then you have these forces which is concrete one, let's say other way around. So the concrete one going compression like this, and the tension one is going like this. So this one is, let's say 616,000 Newton, which is top Rio, and the concrete one is 7994.336 dN, right? So that's equilibrium, and this is by the way 3, 4, 5, 6, 7, 8. This is the 8 Rio at the bottom, and these are concrete. So you have three forces, and there is a one unknown sitting here, dN. So if I just simplify that, I would get dN equal to 149 millimeters. Right. Now this dN is saying that, okay, you have these concrete beams. Now this dN is sitting somewhere here. Let's say this dN 149 millimeters. Now that dN that you calculated is not correct. Why is not correct? Because that is not correct because this is saying that this one should be at the yield, right? We make these assumptions, right? If it is at yield only and only, that dN is correct. Now let's check if that yielding is correct, then we accept this dN. This dN we can accept it only if the top Rio at yield point, right? If it's not, then this dN value is not correct. We need to do the iterative process in that case. Now let's check it out. Let's say we draw this. There are 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm not drawing the spacer bar. Now let's draw this strain diagram here, and there is one more here. Now this is ESC, this is EST, and that is 0.03 concrete. Okay, now let's calculate this ESC, the strain in the top Rio. How are we going to calculate? Because dN value we already know for this case is 149. This is dN, just we calculated, right? That is here. Now let's take in triangles here. That let me see how we're going to take the triangles. ESC divided by, okay, so that's good. Okay, now let's say this ESC divided by this distance. How are we going to get this distance? Because that distance would be 149 millimeter, take away 84 millimeters. Where this 84 coming from? You remember that DSC we calculated, right? That is the depth of the top Rio. Where we calculated. Yeah, there you go, 84 millimeters, right? So that 84 millimeters I just plug here. So these triangles which I take it, that horizontal distance divided by this vertical distance. There is an equivalent triangle here, 0.03 similarly divide by 149. I hope you understand that. So if I redraw these two triangles differently, that is 0.03 and you have 149. And there is a one more little one which has the same angle, but this distance is 149 take away 84, and that is ESC. So this divide by this. So that is first one, they equal to this divided by this. So if I want to calculate ESC, in that case 0.003 times by 149 take away 84 over 149, you will get 0.0013. Now let's check it out. Yield strength of the steel with the 500 megapascal of steel over 200,000 megapascal of yield strength, you get 0.0025. Now the strain in the top Rio, which is 0.0013, is less than yield strength 0.0025 ESY. Therefore, top Rio is not yielded. Let me write it here. Therefore, top Rio is not yielded. Alright, so this is the blow up here. Blow up meaning this DN, which is 149 millimeters, that we have calculated, because we have put this 500 megapascals, right? We put this 500 megapascal. Now this is not yielded because we assume that this steel is yielded. This is at this point where you have 500 at 0.0025, but we have not yielded. We have somewhere here. We don't know where. So this DN value cannot be considered because the top Rio has not yielded. So now what we do? Now let's try to assume some DN value. Let's say we started DN at 149 millimeters. That was the starting point when we assumed that top Rio had yielded, and it did not work it out. So that's fine. Let's do DN equal to 200 millimeters. Let's take a so what happens? Why I take 200? Because you look, this point that we get it. So if you want to increase the strain in your top Rio, so you have 149 millimeters. So if you increase, then the strain in here will be increased, because the further if your Rio sitting further from that one, the steel start to yield, and then so the further it will go, the strain will be increased, as I will going to show you today. Going to show you here. So let's say DN equal to so let me draw it up here clearly. So let's say you have this DN value here, let's say 149, and let's say this is ESC. You calculate, ESC. We calculate ESC as a 0.0013. Now if I just increase that DN somehow, let's say you put it here as a 200, then your strain value, you can see the space here. You can see this distance and this distance. So that is going to be more than 0.0013. So the strain basically gonna increase. So let's try DN equal to 200 millimeter. Keep in mind DN equal to 149 millimeter did not work. So let's try DN equal to this one. Now ultimate goal is to get this value equal to 0. Right? This is our ultimate goal. Ultimate goal that we need to make this one 0 in a way that, so we need to, this is a puzzles. Puzzles means we need to keep this DN changing until you get this one 0. Right? That's kind of a, so you have this one, that is a target. So somehow we need to plug the DN value in a way that your this one, and keep in mind that top Rio is not yielded, so we can't just do this one. So let's repeat the whole procedure again. Repeat the whole procedure, meaning let's calculate this one first. Let's calculate this one first. ESC strain in the top Rio. ESC, remember what was the equation? 0.03 and then you have this. Remember, this is 149 is a DN, but now we change that DN to 200. So 200 take away 84 over 200. So what would be the strain in the top rear is 0.0017. So look at that. As I mentioned, if you drag your DN down, so your rear sitting further from the depth of the neutral axis, that strain will increase. But the strain has not increased in a way that it will still yield it, because our yield strain was 0.025. So it's still less than 0.025. So still this still is not yielded yet. Right? So that's fine, no problem. So we can't use, so we cannot use FSY equal to yield strength 500 megapascal. So what can we use in that case? So that's fine, sigma FC, you know the Young modulus of the steel, which is stress is equal to, we are using this relation, stress is equal to Young modulus times by strain. So the Young modulus was 200 megapascals times by the strain value is 0.0017. So basically we get that value of 336 megapascals. Right? So we can't use 500, but we can use 336. Okay, that sounds good. Now we can also calculate the steel in the, we can calculate now force in concrete. Remember CC. Sorry, first we calculate the force in the rear, right? Because we know the stress. Now we can calculate the force in the top rear, which is 336 times by the area. I'm just repeating again these steps. Which steps I'm talking about? These steps. That compression force in top rear, instead of 500 we will using this 336, and 1232 is the area. So 1232. So this is the force in the top rear. You will get 413,952 newtons. So this is the force in the top rear. Force in the concrete, we have that equation again. I'm just repeating the steps again, but instead of different dn value, I'm using different dn value, and that was here. This concrete compression force, alpha to 0.802, 32, gamma 0.89, dn now 200 that we're going to use, and 350. All other values are same. So let's copy that from here. So you have stress alpha 2 times by the area is gamma dn b, and we done this one previously, but instead of dn, which is we going to use what we assume. So 32 megapascals times by gamma is 0.89 times dn is 200 millimeters that we assume, and b is 350 millimeters. So in that case we will get 159867.2 newtons, right? So that is the force in the concrete. And force, tension force in the bottom rear, I think is exactly the same, because it has not going, it's not depend on the depth of the neutral axis. So 3616 millimeter, 3616 millimeter square times by, and this bottom rear will be at the yield. Okay, if you're not sure, we can also verify that one at the end once we finalize everything. 0.000 newtons. Okay, now let's check whether is the equilibrium going to happen. Let's say Cc plus Cs minus T equal to how much? So we have these 413,952. 413,952 Newton. That is the compression force in the steel. Let me put CS and CC. And then you have this force, which is plus 1598867.2 Newton. And then finally this force which is in the tension, so 1808000 Newton. So my target is to get 0, but it is not 0, 204819.2 Newtons. See, now let me tell you the whole pictures. That we started Dn equal to 149 millimeters, and the steel is not yielded, top Rio is not yielded, so we can't use that one. Then we said Dn, let's take Dn equal to 200 millimeter, and we did not reach the equilibrium. What equilibrium you get is you have this extra value 204819.2 newtons, right? There are some extra force. I need to make this one 0. I want to read off this 204 newtons. I want to read off that one. So how about if I go approach this way, then this will reduce, right? This force will be reduced. So if I go the neutral axis, because here what happened here, we have this 149 first and it did not work. Then we have this 200, did not work. How about we go in between? In between meaning, how about you have, let's say 150, 200. Let's say you have 150 millimeter, you have 200 millimeters, so you have 50 millimeter gap. So divide by 2. Let's say we go 175. Let's say in between and see what happens. Okay, that's good. Let's try Dn equal to 175 millimeters. Exactly the same steps we're going to follow. We first going to calculate this yield strength of the we will calculate the strain in the top Rio, then we calculate the stress in the top Rio, then we calculate the force in the top Rio, then we calculate the force in the concrete based on that new Dn and T, and we will check whether it gets 0 or not. If it gets 0, we accept that Dn and we make all the checks again. So let's try again. I hope you know the drill now. That I have 170. We tried Dn equal to 149 millimeter, did not work. Dn equal to 200 millimeter, did not work. Now Dn equal to, let's try 175 millimeters and let's see if it is going to work or not. So let's start with strain in the top Rio, 0.03. Dn value is 175, take away 84 over 84. I think I show you this one 3 times. This equation, so you know this value, right? 0.016. So that is a strain in the top Rio. Stress in the top Rio is equal to Young modulus times the strain. Then you will have a stress in the top Rio is 320 megapascals. By the way, still this one is not yielded, okay? Because you have 0.0025 yield strain, right? So it's not yielded, so we need to calculate the stress. We can't use 500. So if you calculate the stress, we have force. So the force is equal to stress times area. The stress we just calculated times by the area. I think you know 1232 millimeter square. You get this one as a 394. It's just repetition, okay? I show you this one before 3 times, okay? We done it for D equal to 149, D equal to 200. We just go strain, stress, force, strain, stress, force, okay? 3 component. This is your top Rio. This is your top Rio. Now let's do the concrete one. CC equal to force in the concrete is alpha 2 FC dash and area gamma DNB. So alpha 2, I think we calculated that one, and 32 megapascals. Gamma is, we also calculated 0.89. Sorry, this is repetitions. This is how the doubly reinforced work, because the Dn is a troublemaker, as I mentioned, 350 millimeters. So we got 175. Please note, this is the only difference. This is the only difference. This is the only difference, okay? These are the 2 difference. All the time we just need to target. All other values are same. There is not much difference between the other values. So if you change those one, your value are changing. 1399008.8 newtons. And now the final is the bottom Rio. The force in the bottom row is tensile. I think they are same, EST, FSY, because it's not depend on your DN. So I think we calculated 108,000 newtons, right? Because this bottom row does not depend on your steel. So let's check equilibrium. That CC plus CS minus T equal to 0. Now CC is this one, 1399008.08 newtons. CS is 394240. 394240 Newton. And the last one does not change, which is 1808000 Newton. So if I do this one is minus 14712.2 newtons, which is again not zero, right? But we have a good news here. Good news meaning, look, this is the zero line that we are targeting, right? This is a zero line we are targeting. When you have dn, let's say this is zero line. When you have dn, let's say this is dn. Let's say this is dn. When you have dn is 200 millimeters, that's we done it, right? That dn is 200 millimeters. Your force is 204819. So when you have dn, your force is 204. How much was that? 204,819.2. Let's say this is the force, that's residual force. Okay, that you need to make it zero. And then when you have a 149, when you have a let's say this is the 149. Sorry, this is 175. 175. We got negative value, which is, let me put negative value here, which is 1 minus 147.51.2. Now we need 0. Somewhere we need 0. So we know that the value between 175, because when you're traveling from here to here, at some stage it crosses 0, right? Because you go positive to negative. Do you agree with me? Because when you use 200, it has positive force residual. When you use 175, it goes 175 down. So it's very close now. It's not far away to, because you can see 14,750 and you have 204. So it's something close to this 175. You can see we are very close to 0. 14,000 is not big compared to 204. So we can't go 200 because 200 is too much. So let's do the interpolations now. Let's say you have 175 millimeters, you get minus 14751.2 the n. If I have 200, then you have 204,819.2 interpolation. So what would be the dn value when we get 0? That's what the question, right? So we can just quickly do it. 200 take away 175 over 204,819.2, take away 14755.12 is equal to this x, take away 175 over 0, take away 14751.2. So if you calculate this x value, then you get the dn value, which is 177 millimeters. Right, so it's almost there. Let's try here now 177 and whether, let's say, it's give you the 0 or not. So let's check it out. Let's say it is give you 0 or not. Okay, so same procedures, same style. That now dn equal to 177 millimeters. Check cc plus cs minus t equal to 0 or not. Okay, same story. We said strain is 0.03. This is, by the way, the strain in the top Rio, which is 177. Take away, look, this is repetition. Okay, we done this is 4 times. I'm showing you. So let's say 0.016. So still it is less than yield strength. So we need to calculate the stress in the top Rio, which is the strain times by the Young modulus. So that will give you 320 megapascals. So the strain, stress, force, let's say CS. The force is area times by the stress, 320 Newton per millimeter square. So you get some Newton force, which is 394,240 Newtons. That sounds good. Concrete compression force is again alpha 2 FC dash, and by the way, this dn only the change, all other parameters are same, 0.802 times by 32, gamma value is 0.89, dn is 177 millimeters, b is 350 millimeters, right? I think we done many times these examples, similar one, the above. So 997.472 newtons, and then you have tension force, which does not depend on your dn value. We done this one many times. So let's check it out. That cc plus cs minus t. So you have 14,997.472 newtons plus we got 394,240 newtons. Take away this 1808000. So you will get almost 1.2 times 10 raised to 3 newtons, which is almost zero. Okay, we can't get it zero because of this rounding errors and all, but it's very close. So let's say we accept dn equal to 177 millimeters. Right, once you solve the dn, then all your checks are good. Now what is the check? Let's check the ductility check. Ductility check. How are we going to make the ductility check? Ductility check would be Ku less than 0.36. We always target Ku equal to less than 0.36. Where is it? So ductility checks is here. They have written somewhere. Oh, here you go. Section with Ku greater than 0.36, then we need to do this one, but we need to make sure that we don't need to exceed this 0.36, otherwise we need to do this one, but we make sure that we don't want Ku value greater than 36. So let's calculate Ku equal to dn on d, which is 177 millimeters over depth is 350 millimeters. So the Ku value is 0.34, which is less than 0.36, therefore it is okay, ductility is okay. We can also do the alternative checks for ductility. For ductility, alternative checks is the reinforcement ratio should be less than or equal to maximum reinforcement. Now, how do we calculate the reinforcement ratio? So the reinforcement ratio, you can calculate area of the steel of tensions, take away the area of the compression over the total area of your, let's say this is total area, which is B and D, and this is the area of this tensile Rio, take away the compression Rio. Now we know this area, we calculated before, take away 1232 millimeter square, and then you have 350 times by 520 millimeters and millimeters. So you get the reinforcement ratio is 0.0131. Now we need to check for these conditions. Okay, we make sure that we follow this one. We don't provide the reinforcement. So now this equation is not given in the standard, I believe. Let me check if it is given. No, it's not given in the standard. It's based on this Ku value, that alpha 2 gamma FC dash. If you like, you can put it in your cheat sheet, that this equation is not given in the standard. So we calculate the maximum Rio. Alpha 2 we already know because we calculated that, 0.89 gamma, 32 megapascal is given for in the example, and 500 megapascal for steel Rio. So we make it 0.0164. So rho value which we calculated was rho value which is we calculated 0.0131, which is less than P maximum, which is 0.0164. Therefore it is okay. So that is one kind of a ductility checks that we make. Now, another checks we need to make is the minimum fluxure capacity. If you come back here, that minimum fluxural capacity is here 1.2 times Z FCT dot F. Okay, and please note this is PE. PE we don't need to consider pre-stress force. We don't need to consider pre-stress force because 0 we don't have pre-stress. So 1.2 Z FCT dot F. So let's say minimum one. Let's get the minimum fluxure capacity that by the way we can go for this minimum Rio one, and so one of them would be okay. So when you do the checks, either you make this check or you can make this check. One of them, if you satisfy, then it's okay. What is basically saying that some engineers play smart and they might say I don't need Rio. So standard say no, you must put some minimum Rio, and you must satisfy this one. So let's go through this minimum Rio one. So if you go back to that clause AST minimum, then you will have a 0. Alpha B D on D square FCT dot F dash on FSY. Okay, by the way, this is here. That is the minimum Rio AST alpha B D D square FCT dot FY BWs. Now what happens to this BW and D? Now this just let's put it here BW and D. So if I bring this one AST minimum on BWD, you remember that one, the reinforcement ratio, that area of the tensile reinforcement over BD. So thus I can say this is rho, right? So therefore I cancel that one. Alpha B is 0.2 is given here for rectangular sections. Sorry, rectangular section alpha B equal to 0.2. Now the depth is given 600 over 520 small d. Now this FCT dot F is 0.6 times square root 32. Where is given? I think if you go back to the section number 3. If you go to this section number clause 3.1.13, you will find these FCT dot F values. Probably we will not finish these examples. As I mentioned in the workshop, I will take you through that these examples remaining one. So 3.39 megapascals. We have 3.39 megapascals over 500. So basically that is your minimum reinforcement ratio, and you get 0.00181. So if you check rho minimum, which is 0.00181, which should be greater than your actual rho. Your actual rho was 0.0131. 0.0131 less than or equal to maximum one that we got it is 0.0164. 0.0164. So therefore it is okay. Now let me stop here. Moment capacities, we will go take you through this